Now we will discuss one problem, and this problem is example 6-8 from textbook, and it is a lengthy problem. Okay, we will discuss it. The arm PQ of rectangular conductor is moved from x equal to 0 outwards. The uniform magnetic field is perpendicular to the plane and extends from x equal to 0 to x equal to b and is 0 for x greater than b. Only the arm PQ possesses substantial resistance smaller. Consider the situation when the arm PQ is pulled to outwards from x equal to 0 to x equal to 2b and is then moved back to x equal to 0 with the same constant speed. Obtain the expressions for flux, induced EMF, and the force necessary to pull the arm, and also the power dissipated as joule heat. Sketch the variation of these quantities with distance. So the diagram relevant here, it is this. So here the magnetic field direction is perpendicular to the plane outwards. That's what those dots show. Okay, and you have that rectangular frame as we were discussing, and PQ is the portion of the conductor which is moved. And you know, in this case, the magnetic field, it exists in the region of space from x equal to 0 to x equal to b. Only in this direction or only in this much region of space the magnetic field is existing, and in this space the magnetic field is absent. So from x equal to 0 to x equal to b there is magnetic field. From x equal to b to x equal to 2b there is no magnetic field. And we are asked to find the expressions for induced EMF and the current, force experienced, and the power dissipated. And we are supposed to draw the graph showing all these quantities when it is moved from x equal to 0 to x equal to 2b. That means the conductor is moved from x equal to 0, that means here, in this way and backwards. For this movement, when it is moved like this, what are the changes in this physical quantities? That's what we have to find and plot as a graph. So first, let's discuss the case with EMF. So first we will see when it is moved from x equal to 0 to x equal to 2b. That means in this way when it is moved. Okay, what about the the flux change and the EMF induced? That's what we are going to see first. So when we find the flux, we know the magnetic field is there only from x equal to 0 to x equal to b. So when it is moved, when the conductor is moved from x equal to 0 to x equal to b, you know the expression for flux is phi is equal to b dot a. Since here b and a, area vector, they are in the same direction, so phi becomes ba. Here what is a? That is the case. Here a becomes L into x, where L is the length of the conductor PQ. Length of the conductor PQ is fixed L, and you know this distance is changing. You know it is rectangular in shape. So this distance, since that distance is changing, that area exposed to the magnetic field, that area is changing, and that area becomes L into x, and hence the expression for magnetic flux when the conductor is moved from P to Q, it becomes BLX. The expression for magnetic flux when the conductor is moved from x equal to 0 to x equal to b, it is BLX. That's what which is given here. That is BLX. That means when x is between 0 and b. Now, when it is moved from x equal to b to x equal to 2b, okay, from here to here, when it is moved, in that case, the magnetic field in link with this framework is remaining constant. There is no change in magnetic field, and hence there is no change in magnetic flux also when the conductor is moved from B to 2B. Okay, from when it is moved from B to 2B, the constant magnetic field is in linked, or it is in contact with the framework, and hence the expression for magnetic flux, it becomes BLB. So that is a point to be noted. So when the conductor moves from x equal to 0 to x equal to b, the expression for flux, it is BLX. And when it is moved from x equal to b to x equal to 2b, the expression for flux is BLB. It is because of the fact that when the conductor is moved from B to 2B, there is no change in magnetic flux. So when we think about the backward motion, that means when the conductor is moved from x equal to 2b to b, as we stated now, there is no change in magnetic field linked with the rectangular framework, and hence the expression for magnetic flux remains the same as BLB. Okay, the expression for magnetic flux, it will be BLB when it is moved from 2B to B. That means from here to here, when it is moved from in this direction from x equal to 2B to B, when it is moved, the expression for flux, it is BLB itself. Then when it is moved from B to 0, when it is moved from B to 0, the expression for flux, it will be BLX, because there is change in that distance and the area exposed to magnetic field also is changing. So the expression for magnetic flux, it becomes BLX. Okay, so when we consider all these things and when we draw the graph for the flux, we will get the graph like this. That is the first graph. When on x-axis we have that x equal to 0, so these lines, vertical lines showing, they are this particular point, it is 0, that is origin, and this is B, and this is 2B, and the next point, it stands for the backward motion, that is this is B and this is 0. This is how we are plotting, or we have taken the points on x-axis. Okay, and y-axis we are taking the quantities EMF, force, etc. as we discussed the physical quantities. So in the first case, as we said, from 0 to B, there is change in magnetic flux, that is BLX. So that is why we have a straight line graph like this. And when x equal to B, it becomes BLB, and thereafter when it is moved from B to 2B, the flux is remaining the same, that is BLB. So that is why the graph is parallel to that x-axis. And for the backward motion, again 2B from B, that means from 2B to B, the flux is remaining the same, that is BLB. And when it is in backward motion, again the flux is becoming BLX. And this time, this x is decreasing, and so the graph has a negative slope like this. In the forward motion, it was a positive slope, that means flux was increasing, and in the backward motion, the flux is decreasing. So the slopes of the graphs are different. In our first case it is positive, and in the second case it is negative. So this is the graph showing the flux. when the conductor is moved from x equal to 0 to 2b and backwards from 2b to 0. Now we will discuss the case with the EMF. First we discussed the flux, and after that we are discussing induced EMF. You know what is the expression for induced EMF is? Induced EMF is epsilon is equal to minus d by dt of phi b. And you know phi b is BLX for the range. So always that range of x, it is remaining the same. You should note that. That is, first case it is between 0 and b, and you know in the case of 0 and b, you know the flux is BLX. So we just take d by dt of BLX, that is d by dt of BLX, it is the same as BL into d by dt of x, you know dx by dt is V. So we have the expression for induced EMF as minus BLV, where V is equal to dx by dt. And you know from B to 2B, since the flux is BLB, the flux is constant, there is no change in flux, and hence the induced EMF will be equal to 0. So from the range B to 2B, the induced EMF is equal to 0. So that this is for the moment from 0 to 2b. So when we think about the backward motion, you know from 2b to b, we'll have again the induced EMF to be 0, and from b to 0 we'll get the opposite thing. That means it is moved in the backward direction, and we will get the expression for epsilon as what BLV. It will be equal to BLV. So by plotting these things in the graph, we'll get the graph to be like this. For the forward motion, so you have to note the case for the forward motion from 0 to B, the EMF is minus BLV, and for the backward motion, that is from B to 0, is the EMF is BLV, that is positive. The rest, the EMF is 0. You can see that here the EMF is 0 because there the flux is remaining constant. Hope you followed the graph. Now we move on to the next thing. That's what we have to find, that is force. So first of all, you know the force, we need to find the expression for force, that is the force required to keep the arm PQ in constant motion, and that force is IL cross B, and in this case IL cross B, it becomes ILB. So its direction, it is towards left when it is moved from 0 to B, because the force experienced or force experienced by the conductor. So that BIL we are finding, or LIB, in whatever way you can take, we will just substitute for B and I. That means B is B as such, L is L as such. What is I? I is just epsilon by R, where R is the resistance of that conductor PQ. It's given in the question, small r is the resistance. So we have the expression for force as BLV by R into L into B. So we have B square L square V by R. That is in the limit, that is when the conductor is moved from 0 to B. So we have this as the force, and when it is moved from B to 2B, since there is no EMF, no current is flowing and no force is being experienced. So in that case F is obtained as 0. So for the backward motion also we will get it to be the same. That is when it is moved from 2B to B, force is equal to 0, and for the backward motion from B to 0, the force changes its direction. That means it becomes towards right. So that is to be taken as negative. So when we plot it in the graph, we'll get the graph like this, the third graph. In the third graph only we have the force in that y-axis. So for the motion from 0 to B, this is the force, and for the motion from B to 0, this is the force. This is the force. Okay, and in between the force is 0 because there is no induced EMF. Now moving on to the last physical quantity, which is the power delivered. Power is given by F dot V or I square R. That is what power dissipated as heat it is asked. So we have I square R. So just square current and multiply it with R. So we'll have B square L square V square by R. Since we are taking I square, here we will get for both motion the power to be in the same quadrant. There is no change in quadrant because sign remains the same. So in the upward portion itself, the rest all you can see the change in direction or the change in quadrant we have shown. It is as per the direction of induced EMF. Here since we have I square term, here it remains the same. So this is a point to be noted. That means in all the three graphs we have the portion from B, that means here this the quantities they are having the values 0. Okay, so only for the motion from 0 to B and backward, that is from B to 0, you have the quantities. So only this much for today. With this we conclude. Thank you.